Next speaker is already up. Next, we have Yasamin Eslahi. She is a research assistant at ZHW and a PhD student. She did her master's in data science in the Swiss Joint Master Program, where she got more interested in semantic web and natural language processing. Currently, she works on recommender systems in the context of a natural language interface for the database. Yasamin will present two novel and unsupervised web table annotation methods which leverage the context of the tables to better capture their semantics. Welcome.
Hello, thank you. So, welcome to my presentation on annotating web tables through knowledge bases. I am Yasamin Eslahi. This is a collaboration between Exascale Info Lab at the University of Freiburg and ZHW, with the help of my colleagues, Akansha Bahardwaj, Paolo Rosso, and my advisors, Kurt Stockinger and Philip Coudray-Moreau. So, we are going to have a look at our agenda, what we are going to discuss today. So, initially, we are going to see the introduction, so what is the problem that we are tackling. Then, we provide two possible methodologies for the task of web table annotation. Then we are going to run experiments against two publicly available datasets for the task of web table annotation. And we compare them against two available baselines. And at the end, we are going to conclude. So what is the problem? You know, we have multiple millions and millions of web tables on the web. They're a very rich, structured source of information. Oh, that's awesome, so let's use them. But what is the problem? The problem is that we don't have enough information, the exact information on the specific entities on those web tables. But then what can we do for that? To solve this problem, hopefully we have something called knowledge base. For our knowledge base, what is it? Knowledge base is a structured, rich pages that have information about every entities and their mutual relations and also their metadata. So in the web table annotation task, what we are going to do is to just connect these two elements that we have and provide the annotations for these specific cells. And this can be used for multiple information retrieval tasks. To make it more clear, let's have a look at the table that we have on the left. In this table, as you can see, we have a column called country. It is clear that this column shows the main purpose of the whole table, and we call this column a label column. So let's get more precise on the 7th row, United Kingdom. Imagine that I want to annotate and I want to disambiguate this United Kingdom. So I search it in my surface index form, and I see, oh, we have one country as United Kingdom, and also we have one music album as United Kingdom. So what is the correct one? This is what we are going to answer in here. So we present two different methodologies. Our first method is context lookup, and the second one looping. In the context lookup, what we are presenting is a majority-based method that uses all the candidates and all the types of these candidates from the entities. And what we are presenting in the looping approach is an iterative graph-based approach that uses the embedding of the entities in order to provide the annotation and disambiguation. So we will look at them more precisely. What is our context lookup method? Our context lookup method is divided into two different sections. The first phase, we start by gathering the information about it, and in the second phase, we are trying to annotate by the information that we extracted in the first phase. So, in the information extraction phase, we start by pre-processing the table, detecting what is the main column of this table that we discussed, we call it label column, and find the relation between this column and all available columns in the table. Then we get the entities that we want to annotate, and we extract the types and description tokens of these entities from the knowledge base. And then after one iteration through the whole table, we extract, okay, out of all the types that we have, what is the most frequent type and what is the most frequent description token on the whole table. Good, now that we have this information, let's go and annotate the entities that we have. So if we have only one candidate for an entity, that's perfect. That's the correct annotation, and we annotate the entity. If not, if we have multiple candidates available, then we have to somehow filter them. That we filter them by the information that we have from the first phase, which is the types and description tokens. So we choose the one that has one of these types. And if no result comes out, it means that probably we had a dictation error, that in this case we apply a edit distance function. So to have an example of what we're exactly talking about, look at the left top. We have an example of a web table, which is about the countries. So we start by pre-processing the table, and we extract the textual columns. And in the next phase, on the top right, we say, OK, what is the main column of this table, which in this case is country, and what are the relations with other columns, reference columns? Oh, OK, there is a capital relation. Then we look for these entities that we want to disambiguate and annotate in our surface index form, and we get the possible candidates as well as their types and description tokens. So by having the types and description tokens, after iterating through the whole table once, and we finish the whole table, we say, OK, what is our frequent type? In here, for example, it could be country, city, capital, etc. As well, the same goes for the description token. Here, we finish the first phase. We go for the second phase. What do? We use the types that we extracted. Let's make it more clear. For example, look at the entity Switzerland. In here, we have only one candidate with the type country. Perfect. That's our annotation. Another example, our entity United Kingdom has two possible candidates, but which of those are from the types that we previously extracted as most frequent types? OK, perfect, we have country, so that's the correct annotation. And as we said, if we don't have any candidate for an entity to disambiguate, we apply a distance function and we repeat the annotation steps again. As our second method, we propose a method we call it looping method. What we do in here is that after extracting all the candidates and pre-processing, we look for the candidates in the surface form for all these entities. Then, having these entities, we generate our first looping graph. What is the looping graph? Looping graph is generated from all the candidates all the entities that we are sure about, so they are not ambiguous at all. Then, by having this unambiguous graph, we iterate through all the ambiguous entities, and one by one, for each entity, we add their possible candidates in a graph. Then we apply a ranking function, and by that, we can choose the node with the highest rank. Just beforehand, we check if this entity that we want to add to our graph, it contains all the possible, it contains the context of a web table, which means the type that we already extracted. Then in the next iteration, we already know that, OK, this entity is annotated, and we go to disambiguate another entity. So we have an example for that. So, sorry. OK, in here we see an example that we have 5 nodes already annotated, and all the blue ones, and then we want to annotate an entity called United Kingdom. In here, because we have 2 candidates for United Kingdom, we create a 2-parted graph, and then we calculate the weights of the edges by the cosine similarity between the embedding of these nodes. Then we apply a ranking algorithm, and we choose the node with the highest rank. As we said, we check again for the type, and then if this type existed, is the context of a table, we add to the initial looping graph, and we continue for all the ambiguous nodes. So what we to run our experiments, we run it on 2 different datasets publicly available. The first one is a T2D dataset with 233 tables. This is a dataset with the least sparse values, is not sparse, and also it contains 46 relations in the table. On the other hand, we have a refined Limay dataset, which contains 399 tables. This dataset was initially called Limay, and we took it and we manually edited and augmented this dataset by editing the wrong annotations and also add the missing ones to the gold standard. In total, we add around 3,000 new entities to the gold standard. And we need baselines to compare our algorithms against on these 2 datasets. So the baseline that we are using is from another paper from Rodrigo Moore, which is first we have one baseline for our context lookup method and another one for our embedding method. So lookup baseline is the text-based approach that uses the entities and types in order to disambiguate and then applies the various search strategies based on the number of candidates, while embedding methods are this embedding baseline that we use is a graph-based method that uses the embeddings of the entities, and by a ranking function it annotates. So first we see our results against the lookup baseline on results from the context lookup. So as you can see, in case of a T2D dataset, the baseline is performing better. That's initially because in the T2D dataset, we have significant number of candidates which are unique. And also, we don't have much dictation problem, and it's quite straightforward. So in most of the cases, the first entity, or with high chance, the first entity is the correct one. That's why the baseline is performing better. While in case of Limay dataset, because in many cases we have the mismatch between the text that comes in this web table and the text that comes in our knowledge base. So because of this mismatch, it is not always, we have to maybe many times take the correct candidates or even initial candidates with the distance function. So we have more error in this case. And then it is better to use the types that we have available in all the candidates. So, and also to see our results against the embedding baseline, so our looping method against embedding baseline, as you can see, both approaches are performing significantly better in terms of our proposed method, because the looping method focuses really more on creating the initial graph, which is correct and uses only unambiguous nodes in the initial graph, and it is so much more strict in order to choose the next disambiguation in each iteration. And also, we run an experiment as an extension of this looping method. So we ran once the looping method by having initially having the Levenstein candidates. So we build the looping graph. If the candidate that comes from the Levenstein edit distance is only 1, we add it to the initial graph. While in the second one, even if it is only 1 candidate, we don't add it to the initially created looping graph. So, and as you can see, we achieve 12% better F1 measure in this case. But to be mentioned that even in case of the second result that we are showing, we still use the Levenstein results, but in the later phases that we have more filter on it. And this difference between the numbers and better performance comes from the fact that even if Levenstein distance or any other distance functions are useful, it is better to be more careful about them because they can have multiple errors at that time. And to conclude, we investigated the problem of web table annotation, and also we introduced 2 disambiguating methods for the web table annotation problem. First, we called it the lookup-based context lookup method and also the looping method. The context lookup method was using the types and relations in the web table. in order to select the best candidate, while the looping method was mainly focused on the entities, the semantic entities, and the embedding of those entities. And as we showed already in terms of embedding methods, which we called it lookup, we achieved 18% improvement in terms of F1 measure, and also 24% in terms of precision. Then at the end, we also contribute by presenting our refined version of popular limerick gold standard, where we annotated we changed many wrong annotations in the gold standard, and also we added the missing values. So this project was part of my master thesis, and I want to give my special thanks to Paolo Rosso and Akansha Bharadwaj. And thank you for listening to my presentation, and I'm available if you have any questions.
Thank you very much. How was it to present in front of cameras instead of an audience?
Well, I would like to have the feedback, you know, when you see the faces, it's more clear when you have more motivation maybe to see the audience. But yeah, that was a good experience, I think.
Well, I can't offer feedback, but I can offer some questions. So since all the other talks in this session were about digital health, do you see an application of your method in the medical domain?
Yeah, sure. Actually, there are very interesting research on, for example, these are some parts of information retrieval tasks. For example, I saw some interesting talks in terms of building a knowledge graph for the medical domain by their own vocabularies and their keywords. That I think in this case, we can use these methods to specifically use with, for example, we can create an embedding by their own, this embedding methods that we now created by the whole entities of Wikipedia, for example. We could do it only with specific keywords that comes from their domain, and do the entity annotation for many tasks in their cases as well, I think.
Mm-hmm. Can knowledge learned in a language be transferred to another language?
Sure. We have, this was not the focus of this project, but we have, for example, multilingual embeddings that we present the same concept that we have in this case to the multiple languages. And interestingly, this is not the purpose of this work, but interestingly, for example, most of the cases, the same relation that exists between entities in one language exists also in the other language. For example, the distance between two keywords in one language is quite similar in another language, which we can augment the languages that are not so powerful in terms of input corpuses by augmenting them by the languages like English that has very huge corpus available.
Mm-hmm. Was there like any obstacles you had to conquer during your research?
In terms of technical, okay, yeah. Yeah, for example, one of the main problem was that in many cases when we want to annotate, we have a game, for example, that we want to annotate it, or a book, for example. We have Harry Potter book, version 1, version 2, version 3. It is really hard task to annotate between the entities that have same type, same author, same title even, just a little bit of difference. Or also, like let's say about political parties, we have Christian Democrats in many countries in the Scandinavian parts. And there is only one entity that can show that, okay, what is this table about? Even as a person, when I was looking at it, how can I understand what is this talking about? Even for me, it was not an easy task. Imagine for the machine when it wants to understand. So, yeah, I wish we didn't have that much entities with the same look and different meanings. Yeah, but that's how it is.
Thank you very much, Yasamin.
Thank you
I see
so
someone
much.
was waving behind you, so I guess I have to continue, but thank you very much.
Thank you so much.